Conditions for equilibrium.
Conditions for equilibrium. First, we get to know what is equilibrium. Equilibrium is an object at rest or it is moving at a constant speed. Now, there are two conditions that must be met for an object to be in equilibrium.
The first condition of equilibrium is the most net force in all directions must be zero. For an object to be in equilibrium, it must be experiencing no acceleration. This means that both the net force and the net torque on the object must be zero. Here we will discuss the first condition, that of zero net force. In the form of an equation, this first condition is F net is equals to zero. In order to achieve this condition, the forces acting along each axis of motion must sum to zero. For example, the net external force along the type X and Y axis are zero. This written is as net force of X is equals to zero and net Fy is equals to zero. The condition F net is equals to zero must be true for both static equilibrium, where the object's velocity is zero, and dynamic equilibrium, where the object is moving at a constant velocity. Below, the motionless person is in static equilibrium. The forces acting on him add up to zero. Both forces are vertical in the
Tension forces with angles. So I have here an example, a hanging object. On the left side, it is indicated with tension 1 with 43 degrees angle, and on the right side is tension 2 with 55 degrees angle. The object is pulled down due to gravity with mass 43.8 kilogram. Now, the summation of all forces along x-axis is equals to 0. 0 is equals to T1x plus T2x. T1x is equals to T2x. T1 cosine 43 over cosine 43 equals T2 cosine 55 over cosine 43. Now, cancel cosine 43 on the left side. The remaining is T1 equals T2 cosine 55 over cosine 43. Now, let's stop here since we're going to find the value of T2. On the right side, I have here another diagram indicated a Cartesian plane. A point or a dot on the center going down indicated with W. On the left side is T1x and T1y, and the right side is T2x and T2y with indicated angles. Summation of all forces along y-axis is equals to 0. 0 is equals to T1y plus T2y plus negative W, since the object is going down. W is equals to T1y plus T2y, wherein W is equals to mass times gravity. Now, substitute the values. 43.8, which is our mass, and 9.8 meter per square second is our gravity. The total of 429.24 Newton equals T1y plus T2y. 429.24 Newton equals T1 sine 43 plus T2 sine 55. 429.24 Newton equals T2 cosine 55 over cosine 43 sine 43 plus T2 sine 55. 429.24 Newton equals T2 cosine 55 tangent 43 plus T2 sine 55. Now let's extract. 429.24 Newton equals T2 parentheses cosine 55 tangent 43 plus sine 55 close parentheses. 429.24 Newton equals T2 over cosine 55 tangent 43 plus sine 55. That is 317.01 Newton equals T2. To find the exact answer, let us not forget the significant value. So T2 equals 317 Newton. Now, let's go back to our T1. T1 equals T2 cosine 55 over cosine 43. Now, we already have the values of T2. What we're going to do is to substitute. That is equals 317.01 Newton times cosine 55 over cosine 43. T1 equals 248.62 Newton. Looking for the significant values, that is T1 equals 249 Newton.
Second condition. The second condition of static equilibrium says that the net torque acting on the object must be zero. A rotation body or system can be equilibrium if its rate of rotation is constant and remains unchanged by the force acting on it. The magnitude of torque A-axis rotation is defined to torque is equals to distant force sine theta. A child's seesaw shown in is an example of static equilibrium. An object in static equilibrium is one that has no acceleration in any direction. While there might be motion, such motion is constant. Two children on a seesaw, the system is in static equilibrium, showing no acceleration in any direction. If a given object is in static equilibrium, both the net force and the net torque on the object must be zero.
Center of gravity. The center of gravity of an object is the point located at the object's average position of weight. For a symmetrical object, such as a baseball, this point is at the geometric center of the object. But an irregularly shaped object, such as baseball bat, has more weight at one end than the other end. So the center of the gravity is toward the heavier end. The center of gravity of a piece of tile cut into the shape of a triangle is located on the line passing through the center and the apex. 1/3 of the way up from the base. A solid cone's center of gravity is 1/4 of the way up from its base. Object not made of the same material throughout, that is, object of varying density, we have the same of gravity quite far from the geometric center.
Center of gravity is often called center of mass, which is the average position of all the particles of mass that make up an object. For almost all objects on and near the Earth, these terms are interchangeable. There can be a small difference between center of gravity and center of mass when an object is large enough for gravity to form one part to another. For example, the center of gravity of the World Trade Center is about 1 mm below its center of mass. This is due to the lower stories being pulled a little more strongly by the Earth's gravity than the upper stories. For everyday objects, including tall buildings, we can use the term center of gravity and center of mass interchangeably.
The center of gravity of uniform object is at the midpoint, its geometric center. The CG is the balance point, supporting that the single point supports the whole object. In figure 10.7, the many small vectors represent the force of gravity along the meter stick. All of this can be combined into a resultant force that acts as the CG. The effect is as if the weight of the meter stick were concentrated at this point. That's why you can balance the meter stick by a single upward force directed at this point.
That would be all, and thank you for listening.